Hello everyone from Institute of Aeronautical Engineering. Myself Dr. Purushotham Reddy, Associate Professor in the Department of Information Technology. Today we are going to discuss about Hamiltonian cycles. The course objectives of this subject, design and analysis of algorithms are: students will try to learn mathematical approach for analysis of algorithms. Students will try to learn methods and techniques for analyzing the correctness and resource requirements of algorithms. Different paradigms of algorithm design, including recursive algorithms, divide and conquer algorithms, dynamic programming, greedy algorithms, backtracking, branch and bound, and graph algorithms. Here, strategies for solving problems. Students will try to learn strategies for solving problems not solvable in polynomial time. These are the course outcomes with respect to the chapter backtracking. After successful completion of this course, students will be able to utilize backtracking and branch and bound techniques to deal with traceable and intraceable problems. Now we come to first Hamiltonian circuits. Hamiltonian circuits. In these Hamiltonian circuits, first we are going to discuss about basics. That basics are, first we discuss about what is meant by Hamiltonian path. Hamiltonian cycle. Eulerian path. Eulerian cycle. Hamiltonian path. Now Hamiltonian path means, here we say we take one graph A, B, A to B connection is there, C, A to C, B to C, similarly B to D, C to D, C to E, D to E. Hamiltonian path means, so in any tour we travel from at any vertex and we traverse through all the vertices, and again we travel through all the vertices only once. That one is called as Hamiltonian path. That means here, suppose you travel at start at a vertex A and travel to all these vertices, and that one is called as Hamiltonian path. In this Hamiltonian path, here we observe that first we start from A to B, B to C, C to D, E to D. Now here in this tour, here observe that we visit each and every vertex only once. This one is one Hamiltonian path. Another Hamiltonian path is A to C, C to E, E to D, D to B. This is also a Hamiltonian path. We travel here. In this tour, we observe that we traverse through all the vertices only once. Next, we come to Hamiltonian cycle. Hamiltonian cycle means we travel. We start our tour at vertex A, and we travel through all the vertices and again come back to the starting vertex. That one is called as Hamiltonian path. Now here we see that we start at A to C, C to E, E to D, D to B, again come back to A to C, C to E, E to D, D to A, D to B, B to A. Now here, this is a Hamiltonian cycle. Again we come back to the same starting point. That one is called as Hamiltonian cycle. Next, Eulerian path. Eulerian path means, here visit each and every edge only once. That repeating of vertices will be repeated. So here visit each and every vertex only once. The vertex will be repeated. There is no problem. So E1, E2, E3, E4, E5, E6, E7. So here visit each and every vertex only once. Each and every edge only once in the Eulerian path. Now A, E1, C. Now, similarly, C to D, that means E5, E5D. Next, E3, E, E3E, E2, E2C, E4B, E7, E7, E4, E7, E4, E7, and E. Now here we observe that in this tour, here observe that each and every edge repeats only once. So this one here, the repetition of vertex will be occurred, no problem. So this one is called as Eulerian path. Eulerian cycle means again come back to the same starting point without repeating edges. That one is called as Eulerian cycle. Eulerian cycle. Once again, I am repeating this. So first, Hamiltonian path. Hamiltonian path means here in any graph we start at any vertex. We travel through all the vertices, and no vertex is repeated in that tour. That one is called as Hamiltonian path. But we cover all the vertices in the graph. That is the point here. Next, Hamiltonian cycle means we start at some vertex. We travel each and every vertex. We travel through all the vertices. We visit each and every vertex only once, and again come back to the starting point. That one is called as Hamiltonian cycle. Eulerian path means we start at one vertex and we visit each and every edge only once, and again come back to to starting point, or no edge is repeated in that tour. That one is called as Eulerian path. Eulerian cycle means so we start at some point and we travel through all the vertices. We travel through all the edges. Each and every edge only repeats only once. Again come back to the starting point. That one is called as Eulerian cycle. Now we come to this Hamiltonian cycle. This Hamiltonian cycle problem solved by using backtracking. How to solve this Hamiltonian cycle by using backtracking? Here we see that Hamiltonian circuit. Here the given graph is G equal to V comma E. We have to find the Hamiltonian circuit using backtracking approach. We start our search from any arbitrary vertex, say A. The vertex A becomes the root of the implicit tree. The first element of our partial solution is the first intermediate vertex of the Hamiltonian cycle. That is to be first constructed. The next adjacent vertex is selected by alphabetical order. If at any stage any arbitrary vertex makes a cycle with any vertex other than vertex A, then we say that dead end is reached. In this case, we backtrack one step, and again the search begins by selecting another vertex and backtrack the element from the partial solution. Partial solution must be removed. So the search using backtracking is successful if a Hamiltonian cycle is of time. Now here we see that suppose we take one graph A to B, B to C, C to D. Suppose here we see that A to C. Suppose we traverse from A to C. We start from A and we go to C. That means A. So in this one, we traverse through C. Next, we will traverse through C to D. C to D. Now here we see that in this tour already we travel from A to C, C to D. There is no direct road from D to A. We traverse again, come back to the in the same route again. Otherwise, another route is D to A. That means A is repeated one more time. A to B. That means this is not a Hamiltonian cycle. So here A to C, C to D, D to A. It forms a cycle. So here this dead end is occurred here. Now C to B. Suppose we'll take C to B. C to B, B to D, there is no direct route. Suppose we traverse C to B, B to A, it also forms a dead end. It also forms a cycle. So it is also it also forms a cycle, means it is a dead end. Again come back to A to B, B to C, C to D, D to again come back to A. Now it forms a Hamiltonian cycle. So now here in this case, this Hamiltonian cycle is cycle is constructed. Here Hamiltonian cycle is obtained. So this path A to B, B to C, C to D, D to A. Here A is repeated. The A is the starting point. It repeats one time, no problem. But here we visit each and every vertex only once. So this one is Hamiltonian cycle. So A to B, B to C, C to D. This is the Hamiltonian cycle. Next. Now here you see that an example graph is given here. Consider graph G equal to V comma E. Shown in figure, we have to find Hamiltonian circuit using backtracking method. Here in this graph, here we see that this is the starting point A to B, A to C, B to D, A to D. These paths are there. Similarly, B to C, B to D. Next here, B to E, C to E, D to E, D to F, E to F. These paths are there. So this is the given graph. So using backtracking, how to find the Hamiltonian cycle using backtracking? Here we see that one. Now here we draw here A to B, A to C, A to D, E, B to E, C to E, D to E, E to F, D to F. This is the given graph. Now here we see that how to find Hamiltonian cycle for this given graph. Firstly, we start our search with vertex A. So we start our search with vertex A. So A becomes the root of our implicit tree. So firstly, we start our search with vertex A. So A becomes the root of our tree. So we take this A as root. Next here we choose vertex. The vertex B is adjacent to A. It becomes first in lexicographical order B, C, D. So now B is adjacent to A. So A is the root node. First we draw this adjacent node B. So next adjacent node is C. Next adjacent node is D. So write all these things. So first here A is the root node. A is adjacent to B. A is adjacent to C. A is adjacent to D. So write all the adjacent nodes here representing in this tree. Next here in first level. Now here this is the 0th level. This is the first one. In first level the starting node is B. So B is adjacent to, now here you see in that graph, B is adjacent to E. B is adjacent to C, B adjacent to E. So now here we draw. A is the root node. A is adjacent to B. A is adjacent to C. A is adjacent to D. B is adjacent to C. B is adjacent to E. Now the next level, the next node is C. C is adjacent to which node? Here we see that one in this graph. C adjacent to E. C, next here, C adjacent to E, and also C is adjacent to D. C is adjacent to D, C adjacent to E. So in lexicographical order, D. So D. Now, first root node A. A is adjacent to B, C, and D. D is adjacent to B is adjacent to C, E. C is adjacent to D as well as E. Next, D is adjacent to E and F. So in lexicographical order, E is first, so E is expand. So E is adjacent to F. Now E is adjacent to F. Now here you see that E is adjacent to F. Now here we see that in this tour, here observe that A visited, B visited, C visited, D visited, E visited, F visited. F to A, there is no direct route. Again, come back to the same starting point without repeating any vertex. So if here there is no direct route from F to A, so this forms a dead node. This forms a dead end or dead node. Now here we see that. Next we select E adjacent to D. Now it forms a dead end. Now again come back to E. Now here we see that E completed. E is adjacent to F only. Now here we see that E is adjacent to which one? E is adjacent to F. E is adjacent to B. B already repeated. E adjacent to B is repeated. So already in this path already B is repeated. So it is also comes dead end. So again come back to D. D to F. D to F. Now here we see that D to F. F to E. D to F. F to E. Now here in this tour also here observe that A root here vertex A is repeated. Next vertex B is repeated. Vertex C is repeated. Here visited. Vertex D is visited. Vertex F is repeated. Vertex E is repeated. Visited. So each and every vertex visited once. But E to A there is no direct path. So it is also forms a dead end. So again come back to C. C to E. E is adjacent to. Now here we observe that C to E. E adjacent to F and B. B already in that path already completed. So F. F. E to F. F is adjacent to D. D is adjacent to A. So it forms a solution path. So this one is a solution path and it forms a here that Hamiltonian cycle is constructed. So now that path is A to B, B to C, C to E, E to F, F to D, D to A. Now here in this path here observe that each and every vertex repeats only once. That means here each and every vertex visited only once, not more than once in this path. So this one is called as Hamiltonian cycle. Now suppose to come back to here A to B, B to E. Now A to B, B to E. Now here we see that E is adjacent to which vertex? A to B, B to E, E to C, D, F. So E is adjacent to C, D, F. E is adjacent to C, D, and F. Next, C. C is adjacent to. Now, here we see that C. C is adjacent to D and F. So, already E is repeated. A is already visited. So, D and F. D, F. D is adjacent to F. F don't have any direct path from F to A. So, it is also forms a dead end. Again, come back to here. E to D. D adjacent to C and F. C is adjacent to F. Otherwise, here one more thing is there. C to F, F to D, D to A. So it forms a solution path. So this is also a path. A to B, B to E, E to C, C to F, F to D. This is also a Hamiltonian path or Hamiltonian cycle. So it also forms a solution path. So this is also one more solution path. So this is one solution path. Next, we come to another one here. C to E to D, D to C, C to F. It forms a dead end. So A to B, B to E, E to D, D to F, F to C. F to C is path is there. C to A again go back to A. Direct path is there. So this is also a solution path. So it also forms a Hamiltonian cycle. So it also forms a solution path. Next, again come back to E. E to F. A to B, B to E, E to F. F is adjacent to F. F adjacent to D, E, D only. E already repeated, already visited D. C is not visited here in this path. Now suppose you take D to C. D to C is path is there. So C to A. C to A. This is also a solution path. So here also the Hamiltonian cycle is constructed. Next here. So this one A to B, B to C, C to E, E to F, F to D. This is one solution path. Next, another solution path is A to B, B to E, E to C, C to F, F to D. Again come back to A, D to A. This is another solution path. Next, another one is A to B, B to E, E to F, F to D, D to C. This is also another solution path. Now, here you see that there are some more solution paths. Now, A to C. C is adjacent to D, B, and E. That means B, D. So this is the graph now. Here you see that this is A to B, A to C, A to D, D to C. E, B to E, C to E, D to E, F. This is the given graph. Here observe that B to C is also there. So now A to C path, A to C, B, D, B, D, E, three adjacent vertices are there. Now we expand B. B is adjacent to E. So already C repeated, A repeated. E is adjacent to D and F. Now D is adjacent to F. Now here we see that each and every vertex repeated only once in this tour. But F to D there is no direct route. If you come back in another again come back in the same route, any one of the vertex again repeated. So that's why this forms a dead end. Next here come back here. Come back to D. D is adjacent to C. D adjacent to E. Already all these are repeated. Again come back to E. A to B, B to E, E to F, F to D, D to A direct route is there. So now here in this path, we observe that each and every vertex repeated only once and again you come back to the starting point. So it forms a Hamiltonian cycle. So it forms a solution path. This is also one more solution path. That solution path is A to C, C to B, B to E, E to F, F to D, D to A. So this is one more solution path. Now again come back to here D. D is adjacent to E and F. E adjacent to F. There is no direct path, so it also forms a dead end. Next again come back to here. D to F. F is adjacent to E. So it also forms a dead end. A to C, C to E. E is adjacent to B as well as F. B, D and F. Now here we see that now B is adjacent to C. C already visited. A already visited. So it forms a dead end. E to D, D to F. F to there is no direct path to A, so it forms a dead end. Next we come to F. E to F. F to E. E to D. Here also B is not visited, so it also forms a dead end. So now again come back to A and we traverse in another way, that is D. A to D. D to C is adjacent, E is adjacent and also F is adjacent. D to C. C is adjacent to B, E, B, E. Now B is adjacent to E, E adjacent to F. So again F adjacent to D, D again it repeats. So it also forms a dead end. C adjacent to E, E is adjacent to F. F adjacent to D means D again repeated, so it also forms a dead end. Again compact. E. D is adjacent to E. E is adjacent to F. F is adjacent to, is not adjacent to C or B, so it also forms a dead end. D adjacent to F. F is adjacent to E. E adjacent to C. C adjacent to B. B is adjacent to A. So again come back to A. So it forms a solution path. So fifth one is A to D, D to F, F to E, E to C, C to B. This is also a solution path. So in this way, we find different Hamiltonian cycles for the given graph by using this backtracking. By using backtracking for the any given graph. So now here we see that here we form the backtracking by using any given graph. By using this backtracking. These are the 5. So for this given graph, here we get 5 different solutions. The first one is A to B, B to C, C to E, C to E to F, F to D. Another one is A to B, B to E, E to C, C to F, F to D. Another one is A to B, B to E, E to F, F to D, D to C. Another one is A to C, C to B, B to E, E to F, F to D. Last one solution is A to D, D to F, F to E, E to C, C to B. So this one is a Hamiltonian cycle. How to find the Hamiltonian cycle by using this backtracking. Now, from backtracking, the vertex adjacent to E is BCD, and from which vertex F has already been checked, and B and B, C, D have already visited. So again we backtrack one step. Now the vertex adjacent to D are E, F, from which E has already been checked, and adjacent to F are D and E. If E vertex revisited, then we get a dead state. So again we backtrack one step. Now adjacent to C is E, and adjacent to E is F, and adjacent to F is D, and adjacent to D is A. Here we get the Hamiltonian cycle has all the vertices of that of the vertex other than the static vertex visited only once. That one is A to B, B to C, C to E, E to F, F to D, D to A, and also some other paths also already shown in the previous slide. So this is the final Hamiltonian cycle which we get. Already we discussed about a different type of Hamiltonian cycles in the previous slide. So again backtrack, again come back. So now here we see that here we get again, here we go, come back, backtrack again. Here F to D, it also forms a dead end. Again backtrack. So now here we get solution. So A to B, B to C, C to E, E to F, F to D, D to A. Here we have generated one Hamiltonian circuit, but another Hamiltonian circuit can also be obtained by considering another vertex. Next, you come to this algorithm. Next of K. Now algorithm next of K. The next of K, it is used to find the next adjacent vertex of the present vertex which we choose, and for that vertex we choose the adjacent vertex. For example, here we see that we take the graph like this: A to B, A to C, C to D, B to C, C to D, E, F. Suppose we take this graph. This one is, suppose we start from A. Here we find the next vertex, that means the adjacent vertices of BA that adjacent vertices are B, C, D. Now we choose the next vertex as B. So for that one, we use this algorithm. Algorithm next value of K means we choose the next vertex. Already we choose first vertex A. A is adjacent to the three vertices B, C, D. Among this B, C, D, which one we choose? The next vertex. Generally in lexicographical order, B is the next vertex we choose. For the chosen we use this algorithm. Now here we see that x of 1 to k minus 1 is a path of k minus 1 distinct vertices. If x of k equal to 0, then no vertex has yet been assigned to x of k. After execution, if x of k is assigned to the next highest numbered vertex, which does not already appear in x of 1 to k minus 1, and is connected by an edge to x of k minus 1, otherwise x of k equal to 0. If k equal to n, then in addition x of k is connected to x of 1. So in this way we are connecting that vertices, adjacent vertices. Now here we see that first here repeat function is used to repeat that values, find the repeatedly find the next vertex of the current vertex. So for that one here x of k equal to x of k plus 1 mod n plus 1. Using this value, mod value, to find the next vertex. Now if x of k equal to 0, then return. X of k equal to 0 means no vertices are available after this vertex. So that means we return the vertices which already we visited. If g of x of k minus 1 comma x of k not equal to 0, then so this one means there is some edge there. So if for j equal to 1 to k minus 1 do. So repeating for the vertices, if x of j equal to x of k, if x of j equal to x of k means that vertex is repeated, already visited, again we are repeating that vertex. In that case, we take the break. If j equal to k, then the vertex is distinct or not, here we check. If the vertex is distant, if k less than n or k equal to n, and g of x of n comma x of 1 is not equal to 0, then return. So if that vertex is distinct, we are not visited previously, we forward to next vertex, like that we find. Now here we see that this is the first one, this is second one, this is third one, this is fourth one, fifth one, sixth one. Here x of k, x of 2 equal to x of 2 plus 1. X of b means 2. 2 plus 1 mod n plus 1. So 2 plus 1 means here x of k 2 plus 1 means 3. 3 mod n plus 1. N means totally 6. 6 plus 1 is 7. 3 mod 7 means we get 3. That means we choose this b as a second vertex. So like that we choose the second vertex by using this formula. Now here in this one also, here we see that how to choose the next vertex by using this algorithm. Here we see that first here we choose the vertex A. A has 3 adjacent vertices B, C and D. B, C, D. Next here, which here in lexicographical order we choose next vertex B. So we choose next vertices. B has adjacent vertices as D, E, and C. So like this, we choose the next vertex. Among this, in lexicographical order, C is the next vertex. So we choose C. So like this, we use this next value algorithm for choosing next vertex. Next one is Hamiltonian graph algorithm. Now here we see that Hamiltonian of k. Hamiltonian of k means it has k vertices. This algorithm uses the recursive formation of backtracking to find all Hamiltonian cycles of a graph. The graph is stored as an adjacency matrix G of 1 to n, comma G of 1 to n, all cycles begin at node 1. First to repeat, generate values for x of k. First next value of k, assign a legal next value to x of k. If x of k equal to 0, then return. If x of k equal to 0 means there is no next vertex. If k equal to n means here again we come back to the starting vertex. Again we come back to the starting vertex means we get the Hamiltonian Hamiltonian cycle. That means the Hamiltonian cycle is constructed or obtained. So write that that path, that Hamiltonian cycle values, that vertices which are included in that Hamiltonian cycle. We write that that Hamiltonian cycle vertices. Else Hamiltonian of k plus 1. So repeating for the remaining vertices until false. That means until visiting all the vertices, we repeating this process. For example, here we see that we take the graph A to B, B to C, C to D, E, D, B to E, C to E, D to E, F, E to F, D to F. First we start from A, A adjacent to B, A adjacent to D, C, D. B is adjacent to E, C and E. We choose next vertex of C. C is adjacent to E, E adjacent to F, F is adjacent to D, D to A. So it forms a Hamiltonian cycle. A to B, B to C, C to E, E to F, F to D, D to E. So this forms a Hamiltonian cycle. So we stop here. Otherwise, suppose any dead end is occurred, again backtrack. This one is called as Hamiltonian cycle. So in this way, you find the Hamiltonian cycles by using this backtracking method. Thanks to everyone.
Like, share and subscribe. Hit the bell icon for more updates.